All right. So this looks like a 10.6 example 10.6 of a book Kimmerly Haight Engineering Circuit Analysis. So let's solve this thing. I have the library manager test class. I'll say file new cell view and I'll call it Haight chapter 10 example 10.6. I'll just name it like Haight 10 schematic open. Yes. Okay. So what do we have? We have two resistors. So I'll instantiate in an analog library a resistor. I'll bring a resistor here. So we have a resistor here and we have another resistor here. And then instantiate a capacitor, rotate it. Capacitor is here and rotate another capacitor is here. And then instantiate an inductor. Inductor rotate, it's in series with capacitor. That's it. Two resistors, two capacitors, one inductor. Two resistors, two capacitors, one inductor. Okay. Fit. At this moment, I'll hit the check and save button. Okay. So there are warnings, yeah, because I haven't connected anything. So after that, I'll bring in the wire. I'll instantiate the ground. Let's put the ground here. Bring the wire. Okay. So I have, and there's a voltage source. Okay, so at least my circuit is now saved. So I'll bring the voltage source. I'll instantiate a voltage sine. So this is a sine. Now this thing is representing a sinusoidal voltage. Okay. $200 millifarad and 2 Henry. So Q, and then it's 200 millifarad and 500 millifarad. This one is Q 500 millifarad. 6 ohm and 10 ohm. So this one is 6 ohms. This one is 10 ohms. And inductor is 2 Henry. Q is 2 Henry. And then the voltage source, Q. Okay, what is the voltage source? It says that voltage source, here. Voltage source is 40 sine of 5t. So we know that it's a sine of omega t, so omega is 5 radians per second. So the frequency is 5 divided by 6.28 hertz. So remember, these frequencies are represented in radians per second, and in cadence we have to specify them in hertz. All right. So I'll go. Frequency is 5 divided by 6.28 hertz. Initial phase of sinusoid. So right now, the phase is not important. I'll tell you why. It's 40. So amplitude is 40. So the initial phase of the sinusoidal wave is not important here. It's not important because the phases through each and every component is relative to the voltage supply. So since we only have one voltage supply, so all the phases becomes relative to that. No matter, I mean, if it starts from 0, if it starts from 90, 100, whatever, wherever it starts, all the phase angles through the components becomes relative to that all the time. So if it starts 0, I don't know. I mean, for example, if the current through 200 millifarad is 50 degree, if the voltage source is starting at 0 degree, then the current through the capacitor is 50 degree. Now, if it starts instead of 0 degree, it starts at 40 degree, then the current will become 90 degrees. So it will always be the same value. So that doesn't matter. So I'm not putting your phase of sinusoid if you would like. I mean, if I like, I can use 0 here. Okay, I'll just hit. So my voltage source has now been defined. So circuit has now been defined. What I'm going to look here, so I'll be looking at the voltage of the source, which is the voltage across R1 and the current through R1. Similarly, I'll look at the voltage and current through the capacitor, through this inductor, through this resistor, and through this capacitor. So I'll be looking at the voltage and current angles through each and every component. And of course, to verify this, I have to look at the answer. If we are getting the 6.15 amp with an angle of 49 degree in relation to the source, the supply voltage. Okay, let me check and save. Okay, let's launch the ADEX cell. I'll create a new view, say okay. Yes, that is what my question example is. I'll create the test. Okay. Setup, environment setup. It should be 64-bit. Okay. And AC. Sorry, the transient response. For the transient response, I will say 50 seconds. 50 seconds is a long time, right? One should expect the transient response to die within few seconds of the of the working. So based on that, I'm just putting, I don't know, 50 seconds. Okay. Now there's a new way of saving. So all the outputs. So what we were doing, sometimes we were selecting the outputs from the design. In the other times, we were selecting them. We were entering the whole circuit. Now this is the new way where we would like to save all the outputs. All right. So once you have set the transient response, go to the outputs, save all. I'll hit save all. In save all, I'll select for the first line signals to output, save all. And then on the fourth line, device currents, all. And the sub-circuit probe level, just use the number 3. I don't have to go in details of why we have to do it, use number 3, but you will be using number 3 as a probe level number 3 that you'll be using for all the circuits. All right, and then we are done. Okay. Once we are done with that, I'll just close this one. I will run the simulation. Okay, one warning, 0 errors. Okay, simulation is done. So once this is done, now is the time for me to select my output. So what I'll do, I'll hit on none. You see, I'll right click here. I'll say direct plot. Now direct plot what? The transient signal. So direct plot the transient signal. Okay, so that's my the plot window. So plot window is now open, and my schematic came in front. So now I'll have to select the transient signals. Actually, I forgot to label it. That labeling was so important. So let me escape it. Let me use the label. So I'll label this as VS. VS. Okay. and then I'll label this as V out. And I will label this one as VLC. Yeah, that's it. So I've labeled. Now let's choose the, so I'll be choosing the VS. Yes, this is what I want. I'll also choose the VLC. Is it choosing or not? No, looks like it's not. No. Okay, so the labeling is done. So let me just check and save. Sorry for that. I'll go to, and I'll say direct plot the transient signals. Okay, the voltage, yeah, now it has selected. So VS is, I would like to know VS, I would like to know V out, I would like to know VLC. Now, I would also like to know the current through R1, the current through R0, current through the capacitor, and now one word of precaution. As we see that the current is going from the device to the circuit, right? Remember in the first, second lab instructions, I told you that we can select the current by selecting any of these two outer nodes of a component, and the direction of the current is always towards the component. So if I use the top edge, then the direction of the current will be towards the component. So it will be down. But looking at the circuit configuration, I know that the current is being supplied from the supply. So it is going away from the source. So I'll select this one because selecting this node means going, the current is going towards the supply and actually from supply towards the whole circuit. So I'll be choosing this one for the current. All right. Once I've selected them, I'll hit the escape key and my plots are already here. Okay. So all the currents, the voltages didn't show up. Why? VS and V out. Not showing up again. But anyways, before even looking at the voltages, I can see that the current through capacitor 1 hasn't settled down for 50 seconds. So this is something that I was pointing out. For me, 50 seconds was enough of the time for this circuit to have reached the steady state. But looking at the capacitor, you see it hasn't settled down in 50 seconds, so I will never know the current through the capacitor if it has ever settled down. Not only that, looking at this one, looking at the current through the resistor, I can see that even this hasn't settled down properly. You see, it is going through different amplitudes. Uh, where is again? Here. Yeah, you see, I mean, it's having a higher amplitude and then the lower one, and then again higher amplitude. So first of all, I know that my timing is not enough. So I'll have to increase the time. So I'll go back to my ADXL. ADXL, I'll go to the test. I'll double click this. I'll hit the double click this one and I'll increase my time to uh, I'll increase to 150 seconds. I'm saying that because I know that not every value will be able to be, will be settling by 75 seconds or even 100 seconds. That's just my estimation. So I'm just taking 150 seconds because I want to look at the solution and I want to look at the phases once steady state has been reached. And I believe that by 150 seconds, it should have reached. Say, okay, all right. So we have selected it as a 150 seconds. Okay, done. And then again, run the simulation. Simulation time has now been increased to 150 seconds. So I'll say direct plot transient signals. So in the transient signals, I want Vs, I want V out, I want current through this, I want current through this, as well as this thing and this thing. Escape. Once escape is hit, you have all the plots. Yeah, you see, I mean, if you're able to see the pattern of the cyan color, yeah, here, you see, even until this point, we can see a difference in the amplitude. So it is already 90 seconds, and actually, even this 100 seconds, if you see that this one is at a higher amplitude, this is a lower, and then again higher, and then lower. It was still uh, in the transients, didn't settle. But I think 120, 130 is the time when it has finally settled. So now I'll just look at this small window. So now I have run the simulation for a longer time, but actually I'm just taking a very small portion by right-clicking the mouse, and that's what I'm looking at. So I just, out of those 150 seconds, I've just focused on one very small thing. Now let's do it. I mean, let's first of all, uh, we have to look for the voltage and current IT which is going through it. So these are the voltages and the currents, right? So green one is the voltage of the supply having amplitude of 40 starting at certain point, and then the current. So for the current, here we see towards right. So current, if you see, it's almost more than 6 amperes, all right, which is now required, which is our requirement for this to be 6 ampere. So now comparing to the results, now when I look at the result, I know that the current should be 6.15 ampere with a phase angle of almost 50 degree, where the current is lagging voltage supply by 50 degrees. So we can check that in our plots, since we know that the VT is our voltage, is our source voltage, shown by the green color here, and we have the cyan color, which is the current through the source. To check the phase, let's just take a small area. Let me start with a zero, as close to zero as it's possible. Possibly I can here. So let me just take couple of ways, not more than that, so that they are, accurately visible. Okay, so now if I see that these two will define uh, the angle, the phase angle shift between the two signals. So let me just a little bit more. Okay, so that's close to zero now. Okay, so now we know that this area, this half wave is representing 180 degrees, right? And then half of it, which is at the middle of this one, that represents 90 degree. And we know that the 90, so the 90 degrees is nearly 1, 2, and 3 grid squares. So 3 grid squares are representing 90 degrees. So if it's in the middle, then it would represent 45 degrees. But as we see that this wave is not passing exactly in the middle, it is a little bit ahead, which is kind of 5 degrees, tells us that there's a 50-degree phase shift between the two signals. So again, so this is in the middle and it represents 90 degree. So this is three squares. So three of these rectangles, I'm sorry, three rectangles are representing 90 degrees. So half of it, which is 1.5, represents 45 degrees. And since this cyan wave is a little bit ahead and not exactly in the half, so we can safely say it is 45. It's 45 plus degrees, which is like I would say 50 degrees. So thus kind of confirming our phase angle shift for this plot. Now there are more things in a plot that we can do. For example, if I would like to just look at these two plots in a different window, so I'll right click over here and I'll say send to, not send to, move to, sorry, move to new sub window. Okay, and then I'll take this one. There are different ways. So I can either click here, bring it, and just drag it here. And you see we have these two plots together here, and all the rest of the plots are still on the other plot window, and these two are just shifted towards right. Okay, so we have just shifted them. We just shifted them towards right. So this is kind of one manipulation. Now we can also do the similar things from our uh, ADXL environment. And let me just close these because now I'll start looking at the voltages of the. Mhm. Okay, now let me have a look at the voltage and current of the capacitor. All right. So what I will do? Let me just take the voltages first. So I'll go ADXL and I'll say a direct plot, a transient signal, and the transient signal just give me the voltage, which is V out. That's it. I'll escape. And here's the voltage across the capacitor. Okay, so that's the voltage. It has a lot of transients and it settles somewhere here. Now, imagine I forgot to take the current. I mean, there's a one scenario like I wanted to see the current through the capacitor, but I just forgot it. So I don't have to do a redraw and reselect. I'll just go to ADXL. You see that window tells us the new plot will be replacing the old one. So I would say no, don't replace, append. So append to the same plot again, direct plot. I'll say direct plot the transient signals and now give me the current to the capacitor, escape, and looking at the plot, you see now we have voltage and current to the capacitor. They're both same color, so let me just quickly change the color. Okay, I'll just take that window. So for this plot, uh, actually, there's a way I cannot do it because my software keeps on crashing if I do it. It's just that the server is overloaded, but this is the way. This is one of the way. You will select one of the colors here, and that plot will be colored. So you select a plot. So you either double click it, which is not working with me right now, but it should work. It should work. Okay, so you double click it, and it should start working. It should give you the window, the pop-up window, having all the properties where you are able to change the color. Or the other way is, as I said, right click. So select a plot, right click the plot, and then choose a color. Okay, and then the plot will be colored that way. Here, color, and do it. So I don't want to do this because I've checked that it was crashing just when I'm changing color, at least at this time of the day. So let's not do it, but the point is clear here. So I have exported these two plots in a new window, and I just took the voltage through the capacitor, and later I selected the current. So I know I appended the current on the plot. Now looking at the phase shift, again, just have a look at this plot. So this is the voltage, and if you see that this voltage is reaching its peak at this point, and this is exactly the point where the current wave is starting, current through the capacitor. And we very much know that current leads the voltage in capacitor. All right. So uh, the current leads the voltage in capacitor, and by 90 degrees. So we exactly know, since it is in the middle, we exactly know that there's a phase shift of 90-degree between the currents of the capacitor and inductor. Now I can actually do one more thing. So let's look at let me close this window again. Let me go to ADXL. Now, what I would like to do, I would like to find the voltage of the inductor. So to find the voltage of inductor, what I need the difference of VLC minus V out. So the difference of these two voltages will give me the voltage across the inductor. So once I have the voltage and then I can find the current through the inductor, then I'll be able to see the phase angles for this plot. So let's do it. To find the difference in the voltage, all I have to do, let me just uh, okay, let me have a new window. So I'll go direct plot, transient difference. Okay, so I'm selecting transient difference. The transient difference, I'll take the first volt and the second volt. So and then escape, hit the escape key, and you will see the difference here. This is VLC minus V out. Okay, so that is the voltage across the inductor. That's what we got. And now I'll go to ADXL again, and I'll append the transient signal. So direct plot, and sorry, transient signal, and then the current through inductor. So once it is done, hit the escape key, go to the plot, and now you see. So these are the two plots, and if we see here, I mean, if we closely look, that it is nearly almost 90 degree, nearly almost 90-degree phase shift between these two plots. All right. So now we have already checked how the so we confirm that the source voltage and the current through the source are having 6.115 ampere current with a phase shift of 50 degrees. We also check the voltage and current phases of inductor as well as capacitor, and we check different ways of manipulating the plots in a new window, appending to the same window. uh, so now my video, I mean, the tutorial is done. So just before I go, I would try the same thing if it has started working now. Uh, I'm not sure, so we can just try. Oh, it worked. Okay, so the double clicking is working. So I'll say select the foreground color. I'll just take, I don't know, this color. Okay, sorry, okay, and okay. And I have this color. So you select the plot and then double click it, and here's the pop-up window. I'll take this one as the yellow color. Okay, and okay. And now we have these two plots. So beautiful. So that's working. This is all about the lecture today. I hope you guys have enjoyed it.